Second session this morning, and we are having a talk by Pierre Weiss, who is from the University de Toulouse, and we started to see some impulse responses and other interesting engineering concepts, and we are going to continue to see them in Pierre Weiss's talk. So it's estimation of linear operators from scattered impulse responses, slightly different from the title that is appearing there. So the podium is yours.
Okay, so well, first, thanks very much for the invitation. It's really great to be here, and I had the chance to discuss with plenty of wonderful people. So thanks again. Yes, so this is a joint work with Paul Escorn here, who's now a postdoc at Johns Hopkins, and with Jérémy Bigot, who is a professor at Université de Bordeaux. And well, it will be about the problem of spatially varying blur operators. So let me motivate this problem. So I don't know if you can see here, but this is a slice of a microtumor taken with a microscope, and in fact this image is 3D, three-dimensional. And what you see here are nuclei within the tumor, and well, you can see that they are quite sharp here in the center, and when you go to the boundaries of the tumor, they get very blurry. And well, that's a phenomenon that happens a lot in microscopy, and one way to see that is to insert fluorescent microbeads within the sample. So here you are seeing microbeads, and those microbeads give you some knowledge of the way the system degrades your image. It gives you the impulse response of your system at different locations. In imaging, it's often called the point spread function. This is a point spread function. This is another one, and you see that when you move within the sample, the point spread functions are changing. Okay, so that's the same experiment, but in 3D. And what you see here are the different point spread function, and well, it's really, you can see that it's quite complicated. For instance, when you go here, the point spread function becomes just huge, and here they are nicer. But one important thing is that they vary smoothly in space. When you look at two neighboring points, the PSFs are not too far away from one another. Okay, so this problem actually appears in many different fields. So here it's in computer vision, here it's a photograph taken with a camera on a tripod, and here it's the same photograph but handheld. And you see that there are some shiny spots here, and if you zoom on the shiny spots on the blurry image, you see that you are seeing a curve here, and here you are seeing another one, and another one here, and you see that while you move in space, the curves are different. So once again, the impulse response is space varying. So I need to tell right now that I won't really study that kind of operators. This is a very specific operator, but computer vision people don't say it. The fact is that the impulse response here you can see them as measures supported on one-dimensional objects. And in fact, those operators are nearly not compact. Because if you take the Fourier transform of a measure, well, it doesn't vanish in some direction of space. So actually, it's very easy to inverse that kind of operators. It's much harder to deal with those operators that I showed. Okay. Okay. So and here is a last example in astronomy. You are seeing galaxies, and sometimes they are distorted. They are anisotropic. And the reason is that some black holes may distort the straight lines of light, and then it's also creating space-varying impulse responses. And here the problem is really to recover the operator, because the operator, the impulse response, gives you some indirect knowledge about the locations of the black holes in the universe. So now let's go to the setting. So I will work on omega, a domain of RD. This is the space dimension. And I will see my images as element of L2. And if you want to do deblurring, that may look as a standard inverse problem, because you are looking at U0 equals HU plus B. B is noise. H is a blur operator. And in this talk, I will just assume that H is a linear integral operator, so a bounded operator from L2 to L2, which is given by a kernel here, which basically describes the point spread functions at different locations. And but by saying this, I said nearly nothing except that it's linear, because by Schwarz kernel theorem, any linear operator can be represented in this form. So I will need to add more structure to be able to say interesting things. Okay. So on all my talk, I will try to illustrate the concepts with 1D examples. And I will take this simple kernel here. And what is this kernel? So if you fix y and that you vary x, this is just a Gaussian with variance sigma of y. And so there are two ways to represent the operator. The first way is by the matrix. So here I'm just representing this function. And so here you need to understand that here is the y direction and here is the x direction. And so if you fix y and that you vary x, meaning that you are looking at a line here, you should see a Gaussian. The other way to represent the operator, which is not as rich as this one, is to apply the operator to a Dirac comb. And so you will see the impulse responses regularly located on the grid. And so you see that here it's just Gaussians with a variance that linearly increases with space. Okay, so what are the challenges with these kinds of operators? The first very big challenge is about the representation. For instance, a typical image in biology would be 2000 by 2000 by 2000. And if you are very naive and that you want to store your operator as a matrix, well, the size of your matrix is 4 zettabytes. And that's more than all the data collected as of 2014 on all computers in the world. So, okay, those objects are just huge things. So you need very, very high compression and also fast matrix vector product. A second very serious problem is that very often you don't have a knowledge of your operator. You can just probe it indirectly, for instance, by looking at its action on Dirac masses. And so it means that you are able to observe a few scattered point spread functions. So basically it means that you observe your kernel only at a few locations yi, and very often they are noisy. And so one problem, which is serious, is to recover your operator from this partial knowledge. Okay, so my talk will be about these two squares, but now I will tell you about my research program because this is going further. So in practice, I'm working a lot with microscopists. And in microscopy, the problem is when you get an image, you don't really know what operator gave rise to this image. And the problem is, for instance, you have screws to focus your system. And if the biologist decides to turn the screw, well, you will get a different operator. And if you calibrated your operator in advance, it's completely useless. There may happen different problems. For instance, you put the slice under your microscope, and then there is a very small tilt. And well, this will give you also another operator. The temperature changes and so on. But what happens is that a microscope cannot produce any operator. And the idea is that it's defined only with a very small number of parameters. For instance, the focal screw. And so you can imagine the set of admissible operators as a manifold within an infinite dimensional space. And okay, the suite of the program, which I will be able to present in 1 year, I guess, is to try reconstructing this manifold. And here we are working on that quite seriously. The idea is to take many pictures of microbeads. So by using this kind of method, it means you are sampling the manifold, and then you can try to reconstruct the manifold. And then the last problem, which is also quite serious, is in practice you just get a blurry image. And the blind deblurring problem within this frame is to, knowing the blurry image and this low dimensional manifold, try to find both the operator and the sharp image. Okay, so that's the problem. But here I will really concentrate on those two problems, which are the basis. Okay, so the first part of my talk is about the representation of operators. So, and then I will speak about product convolution expansion. So that's okay. So the idea of these expansions is that if you look at two neighboring impulse responses, they should be close in some sense. And if you make this assumption, it is very tempting to approximate an operator H by a sum of operators of this form. So what you do is you are taking function vk, you are multiplying pointwise by u, your image u, and then you are making a convolutions with the function uk. And for instance, if you take vk to be, okay, I will make a drawing. The basic idea, for instance, you imagine that you are working on the square. You take omega is a square. Then you can decompose your image domain into subsquares, omega 1, omega 2, omega 3, omega 4. And so you can take the function vk here to be the characteristic functions of these squares. And the functions uk here could be, for instance, the impulse response at the center of the square. That's the basic idea. And so the interest of this decomposition is that it can be computed fast. This symbol here means that the diameter of the support of your function. So if you're clever, if you make a clever implementation of this with a computer with a fast Fourier transform, you can see that the complexity of computing this will be of this form. So it depends on the support of your function uk and vk, and of course on the order of your tensor. So the questions that arise when you propose such an approximation are how to choose the function uk and vk, what is the approximation error, and how many operations you need to get epsilon approximation. And well, here these norms are norms. In all my talk, this norm will be the Hilbert-Schmidt norm, so just the L2 norm between the kernels. And it turns out that this question was studied a lot in the literature, especially in imaging. So there are many proposals for functions uk and vk. And well, for point 2 and 3, I saw nothing in the literature. So I will tell you about this. So to understand this product convolution expansion, it's very nice to understand the space varying impulse response, which is, well, defined from the kernel like this. So, okay, an image is simpler. All what you do is you take your kernel and you make a shear. You transform it in this way. So basically what you do is that you center all the PSFs exactly at the same location. And the nice thing when you do that is that here you had a near full rank matrix. And when you do that, you really see that this operation should be rank reducing. And so you can do it numerically. So for instance, here the rank of this matrix is, the numerical rank of this matrix is 59. Here it's 12, so you decrease. And here the rank is full. I took a 256 by 256 discretization. And here, if you look at this representation, it's 41. So you are rank reducing. And what is the connection with product convolution expansions? Well, it's quite simple. If you consider an expansion of this form, its space varying impulse response is exactly given by an M-rank tensor. Okay, so that's the connection between that kind of product convolution expansion and the space varying impulse response. So, and that's a key idea, very simple one, but many people disregard this. And in fact, only French people know that. And I could see that only in French, in 2 French papers. And if you look at the imaging literature, most people actually swap the convolution and the product. And if you do that, you completely lose this nice interpretation. And well, you can get no basically approximation theory with that type of decomposition. And really, if you look at least 50% of the papers in imaging do it wrong with this kind of approximation. So you really put the convolution here and the product here. Okay. Yeah. So now I will try to analyze a few methods, and the analysis from a mathematical point of view, it's very simple. So the first idea that I presented was you just decompose your domain into subdomains like this, and the method will work well if you have some smoothness assumption. So basically the idea is that when you go from when you move within the space, your PSF should not vary too much. Otherwise, this kind of approximation cannot work when you just partition the domain and make convolution in each of the locations. And well, one simple way of saying that is that the variations of the PSF when you move in space are Lipschitz. This is this assumption, and you can also assume a compact support of the PSFs. And then in that case, it's tempting to do exactly the kind of decomposition I told you about. And well, the result is that if you want an epsilon approximation of your operator with that kind of approach, which is really the one implemented everywhere in most papers, you need this number of operations. And so there are some good things here. First, you can capture the fact that you have a compact support. So here, kappa is a number between 0 and 1 that describes the diameter of the support. And there is one bad thing, which is the dependency on the precision here, which just scales at epsilon to the minus b. And it means that you cannot really capture the smoothness. You would accept, for instance, that here if you have two derivatives which are bounded, you could expect to have a better rate here, and it's not the case. Oh, so I realized I lost all my references. That's very bad. I don't know what happened. I think I need to recompile it, because otherwise I'm really referring to plenty of things. I'm very sorry about this. Oh. What happened? I don't know. Maybe Acrobat Reader doesn't work with the references? I don't know. It's the first time I use it. I'm on Linux usually. Okay, so I have I found my references again. That's fine. How does it work here?
Slideshow.
Slideshow.
Okay. No, not slideshow.
Okay. 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 So so the first paper about product convolution expansion that I could find was by Trussell and Hunt in '78, and Nagy and O'Leary proposed more advanced methods where they basically use the decomposition here is overlapping, but the way they do it, you cannot prove better rates than this either. And so no, this is not working anyway. Okay. So there is another nice idea which comes from French astronomers here, and here the idea is different. So you take your space varying impulse response, which is given, by this function here, this 2D function. Here you have the y direction. Here you have the x direction. And the idea with these methods is different. It is to assume that each PSF, so if you look at the function in this direction, well, all of these functions could be, when you project them on a low dimensional subspace of size m, you get some approximation rate like this. So here R is a regularity. In all my talk it will be the regularity in the y direction, while S will be the regularity in the y direction. And if you have such an assumption that you can decompose your PSFs on a low dimensional subspace and get a good approximation rate, then you get an epsilon approximation of your function by just taking your function vk of y to be the projection of the PSFs onto this function uk, and then you get a dependency on the regularity of your functions basically. And so that's nicer in terms of epsilon, but here you lose the fact that you are using you lose something with the compact support. Okay, and so we wondered whether we could do better than this, and the answer is yes. So what I will present now is a bit newer. So when we will assume the following smoothness assumption, which says here that almost every line of your space varying impulse response should be in the Sobolev space HS, so it should have S derivatives in L2. And we will also assume that the point spread functions are compactly supported. Same assumption as previously. Okay, so well, I will skip most of it, but okay, under these assumptions, the first idea that you could have is to use a Schmidt decomposition, so basically a singular value decomposition of your operator, since you know that it's the best way to minimize the Hilbert-Schmidt norm. And if you do that, you get a nice result that tells you that the complexity to find an epsilon approximation of your operator will scale like this. So you get n log n, where n is the number of pixels. Then you have epsilon to the minus d over s, where s is the smoothness. That's nice. And one problem comes from here. You cannot really capture the fact that you have a compact support, because as the smoothness increases, this term will go to 1. And the problem with the Schmidt decomposition is that the functions uk and vk are not compactly supported. There is no reason that they are supported on a small interval, for instance. And so you can wonder whether you can get better than this, and the answer is yes. And here you need to go to wavelets. So I will maybe skip the details, that's a bit technical, but let's just look at the conclusion, and then I will explain. If you take for the functions v mu here a wavelet basis, and that you just keep the low frequency wavelets, then you get this kind of complexity bound, where you keep this dependency on epsilon, this n log n, but here you have a 1, and then it really means that you can take benefit of the compact support. And so I will maybe illustrate this. So the idea is you take your space varying impulse response, and then what you do is each line you compute its wavelet transform. So now this map here is from L2 in this direction. It's in yes, big L2 in this direction and small L2 in this direction. And you see that by computing the wavelet transform in that horizontal direction, what you do is you really compact the information on just the low frequencies. And so you can just keep these ones, and well, this will give you a good approximation. And here I just took a less regular kernel. It looks similar, but it's not. Especially it has a kink here in the middle. And then you see that you will need more. You will need more coefficients. The compression is weaker here, and you will need more coefficients to encode this function because it's less smooth. And this is captured by the theorem. Okay, and last but not the least, I will maybe show the picture. There is a simple idea which consists of taking the wavelet transform in this direction and then the wavelet transform in this direction. And for this, you need additional regularity assumption. You need that your function S, your space varying impulse response, belongs to a mixed double S space, meaning that the derivative are smooth in that direction and S smooth in that direction. And if you do that, well, I will show the picture maybe first. You see that you can get huge compression factors. Here you had those lines were mostly non-zero, but now by doing this, you are really restricting the number of non-zero coefficients to the low frequencies. And in fact, this is interesting because if your aim is to store your operator, not to make fast matrix vector products, you get a representation of your operator which is independent of the number of pixels n. Yeah, meaning that you can store your operator with O of 1 coefficients. So that may be very useful in practice. And the number of coefficients that you need to get a good approximation depend on the regularity both in the x and y direction. Okay. So you can wonder what is the connection with this type of approaches, which are, quite famous. So, of course, evaluating linear operators is a very important problem in numerical analysis. And so, for instance, many methods were developed. And for instance, you have the techniques of Hackbush or Tietyshnikovs. You have the sparse summation methods or the wavelet expansions by Belkin, Kaufman, and Röchlin. And all those methods amount to the same idea, which is to decompose your domain into a multiscale, in a multiscale manner like this. So you have small squares along the diagonal and larger squares as you go far away from the diagonal. And the idea is that if your function is sufficiently smooth, you will be able to approximate the matrix within a square by a low rank matrix. That's really the basic idea behind all those techniques. And here you can wonder what is the connection with what we do, and here it is. In fact, we are doing the same with the wavelet approach, except that now we are making a decomposition well, that is more adapted to the geometry of the kernel. That's really the basic idea behind this kind of decomposition. And the nice thing is that you get good approximation rates with much weaker assumptions on the kernel. That's the strong thing. Okay. So this is the end of the first part of the talk. So we analyzed the popular method in imaging, and the analysis suggested new optimal methods, which are multi-scale. And this is a versatile representation for the identification, which is the second part of the talk. So this is the second part of the talk, and this is based on this paper, which has been submitted to Applied and Computational Harmonic Analysis for like 2 or 3 years, but okay. It should. I think the reviews were very good. So I go to the second part of the talk. So here the idea is the following. Assume that you just observe a few PSFs. So it means that you are observing a few lines of this function here, just a few lines, and they are noisy. And from this information, from these few lines, you would like to go back to here, so to recover your operator. Okay, that's the problem. So here we made a sampling of the operator, and this is we want to reconstruct it. So this problem has actually a long history, and I discovered recently that perhaps the first work was by Thomas Kailat, so the advisor of Alfred. And in there he proposed an idea that I think is very interesting. I can explain in just a few words. The idea is you take this space varying impulse response, and you assume the assumption to use this kind of approach is that if you compute the Fourier transform along the y direction, it needs to be band limited. And operators which have a band limited, which are band limited when you take the Fourier transform here are called. This is called. Okay, the Fourier transform of this is called the Cohn-Nirenberg symbol, and it's very useful in PDAs. Okay, and under this assumption, the nice thing is that if you observe h times the Dirac comb, here the yi needs to be regularly spaced, then you have exact reconstruction formula. And the difference with what I'm presenting is that here you know the action of h on the sum, and not on each individual PSF. So that's a bit stronger here. But unfortunately, the band limited assumption here is too strong for us. And also the reconstruction formula, I'm not sure if they can be implemented in huge dimension. So then there are many authors studying similar problems recently. For instance, you have the paper by Emmanuel Candes about exact matrix completion. But here I think okay, you can never use this, because basically their aim here is to identify the coefficients that will be useful. And you cannot afford to have to identify the coefficients, because you are living in such a huge space that you can definitely not use this. And it's a bit the same for all those approaches. Maybe this one is the nicest one by Jiawei Chiu and Laurent de Manet. But here the main assumption is that you observe the action of your operator on the random signal. And under this assumption, sometimes you can reconstruct it. But okay, it's not what we want to do. So there is another. It's working? No. Okay. So there is another approach which was also developed by French astronomers, which is much simpler, and I will describe it. It works well in practice in rapid computing times, but there is no supporting theory. So I will go to the description of this method. So observing PSFs is not realistic in practice, because you only get a finite number of observations in practice, like in the talk of Michael. All what you can expect is to see scalar products of your PSFs with functions phi k. So in fact, in my talk, I will rather assume that this is the observation model. I don't observe the PSF directly, but I just observe its projection onto a few elements of a basis. And here I assume that possibly I could observe an infinite number of projections, but that's not realistic with a computer. And we observe the PSF at scattered locations, which are described by a vector big Y, which is a set of functions yi. And the PSFs are noisy, and here I will assume a Gaussian noise. So we'll see that some geometrical quantities are important in this problem. And the two important quantities are the field distance and the separation distance. So say you are working on a square and you are sampling your operator on a few points. Then the field distance is the radius of the largest ball that you can put inside your domain, such that it touches no PSF. So that's the field distance. And the separation distance is the minimal distance between two impulse responses, between two points that you are sampling. So we'll see that this plays a critical role. And okay, for the smoothness assumption, I will assume that the space-varying impulse response varies smoothly in the y direction. And okay, basically, I want continuity of the variations of the PSFs. Otherwise, just applying h to a Dirac doesn't have a meaning. The Dirac is only defined. You can only compute scalar products with continuous functions. And so here I assume that all the lines of my functions are in the Sobolev space HS, and I need to, for continuity by Sobolev embedding theorems, I need S to be larger than D over 2. Okay, that's the first assumption. And for the second assumption, I will assume that I can decompose my PSFs onto a low-dimensional basis. So from a mathematical point of view, I need to introduce this space here of functions such that when you take the scalar product with the functions phi k and that you are measuring a weighted L2 norm, it should be less than infinity. And this weight here, WK, should increase like this. So this is really standard in approximation theory. And okay, that's a space of functions. And I assume that this integral is bounded. That's so basically it means that my PSFs are smooth and the variations of the PSFs are smooth. And for instance, here if you take phi k to be a wavelet basis, then this means that your space-varying impulse response belongs to the mixed Sobolev space HRS, which is very natural in applications. Okay. So then when you know that you have those two inequalities, it's natural to introduce this space of vector-valued function f. So it's a function from omega to Rn, which satisfies this inequality. So here it's related to the talk of Michael. Here, this is a Bepo-Levy semi-norm, which is equivalent to the Sobolev semi-norm. So, okay, so here we are basically saying that our PSF should be smooth in both directions, in the R and in the S direction. And this space here of vector-valued function, you can show that this is a vector-valued reproducible kernel Hilbert space for those who know this. And okay, the nice thing about this is that, okay, first, when you introduce this space, it's natural to solve this problem to recover. So, okay, no, I go to the. So you had your space-varying impulse response. Then for each of the columns here, you project them onto your basis phi k, and this gives you a more compact representation of your operator. Okay, so this is an equivalent representation. This is another possible representation of your operator. And then the sampling model is that you just observe a few coefficients in some lines here. And okay, the problem is from this information you want to go back here. Okay. And so the natural thing to do is, since you know those coefficients here, you want that your estimator F hat is close to them in L2 because we have Gaussian noise. And you also want your function to live in the space of admissible operators, so which is the space I have defined previously. Okay, and the nice thing about this is that it can be implemented very rapidly. So the complexity to solve this problem, which lives in a huge space, is just given by this. So small n is the number of point spread functions you are observing. So usually you just see a few, say 100. So the complexity is O of n cubed, and plus n square. And you need to see that here n is not the number of pixels, but it's the number of projections you are making. So usually it's much smaller than the number of pixels. And so this complexity, in fact, you can do the integration in real time. The other nice thing about this estimation is that it gives you an estimation of your operator in infinite dimension. So actually you can show that the operator has this specific form, where the rho k here are splines. So they are radial basis functions, and this is because we have this reproducible kernel Hilbert space structure. And so the whole problem is to find those coefficients alpha here. If you find them, then you get a representation of f, which gives a representation of s and of h. Okay. And for this, the complexity of finding these coefficients is just given by the resolution of a set of n-linear systems. And well, those functions here, rho k, depend on the weights that you put here. But if some weights are identical, you can factorize some matrices, and then this allows to still reduce the computational complexity. Okay, now comes the important slide. So we suffered a lot for this. And that was complicated, but that's just one slice. So the first theorems that we have is that, so at the end we get an estimator h hat of the operator h. And the expectation of the error that you make between both operators is given by this formula. So you have the variance of the noise times the number of PSFs that you observe to the -1. So it means that if you observe many PSFs, well, you will get an approximation of your operator that goes to 0. It gets better and better. And the convergence rate depends on 2q over 2q plus d, where q is given by this formula. And also we characterize this constant c, but it's completely awful. So the only thing you need to know is that it depends on the ratio between the field distance and the mean distance. That's the key fact. And also there is a nice thing about this estimation is that at the end you get a representation of your operator as a product convolution expansion. So you can directly apply it very fast in imaging. The second theorem is also very complicated, but it's just one line. In fact, there is under the assumptions that I made, there is no way to get a better estimator. So you cannot compete with that. No estimator can do better than this uniformly on the class of functions, of operators that I consider in this talk. Okay, so that's two strong results. And okay, that's it. So now I can go to the numerical experiment. So here you see the space-varying impulse response. What you observe is this, and this is what we reconstruct with the approach that I've shown. And this is what the astronomers get. And the reason why they get slightly, you see that it's still noisy here, while here it looks very nice. And the reason why they get this is that they didn't add this regularization of the PSFs in the y direction. This is this weight W of k. So this is a 2D simulation. So this is the operator I consider. So here I just applied the operator. So this is not the matrix of the operator, but I applied my operator. This is a 2D operator now, and I apply it to a Dirac comb. So this gives me the PSFs at different locations. Then I observe a few noisy PSFs, and from this I can reconstruct this. So this is not perfect, but this is something. Okay. And then you can try to use this operator. So you take an image, you blur it with the true operator, and then you can try to deblur it with the estimated operator. And this is what we get. So it's not perfect, but it does something. And now this is a real experiment with a wide field microscope. So this is a 2000 by 2000 image, and I'm working with biologists who gave us 5,000 images of those. Those are microbeads. And so we got 5,000 such images, and from each of these images we can reconstruct one operator. So it means we are and each of these images has been taken in a different experimental condition. So that's about the sampling of the manifold. So, but here I'm just showing the result for one. So you take one of them, And if you look at the PSFs from a close distance, this is what you see. So you see that it's really space varying. Depending on the location, it's really changing a lot. And now, so we estimated the operator, and now this is a real image. This is the deblurred image, so you don't see anything because it's too high resolution. But you can zoom, and here this is a zoom on a result of deblurring with the commercial software Huygens. This is, I think probably the only commercial software for deconvolution or deblurring. Here is deblurring, and here is the result we obtained with our estimation. So you really see that we obtain better details, and this is true uniformly over all the image domain. Okay, so that's my conclusion. So we analyzed and improved the long introduced method in imaging. We also introduced a new operator estimator with theoretical guarantees. And well, we have a few papers ongoing, and that's the end. Okay, thank you very much.
Time for questions and comments.
Yes?
Yes.
So if in your theorem you show the error for the expectation and given the number of visualization of the point spread bar.
Yes.
How about in the deterministic case? Is it possible to tell how many minimum number of PSF you need to reconstruct, or minimum number of realizations that you need to reconstruct the operator?
Yes, so if you have knowledge of if you know how to bound your noise in L2, then we also have a deterministic result, which will depend on the geometry of your...
No noise. If I don't have any noise.
Yes, we also have that. Yeah, we also have that. In the deterministic case, we also have that. Yes, we have it, but then I cannot show you the result, but we have it, yes.
Some more comments? Yes.
Some applications where deblurring is needed, but where the kernels that you use are less local and also have non-local contributions. So that means your flipping or your rotation that you support your theory on is not exactly applicable immediately, and the compression is maybe also a problem. Do you have an idea how to address those problems? So it could be in neuroscience, like the talk we have seen, where you think about kernel estimates. So how to proceed with the compression rates and the nice numerical results when it's getting a bit more to non-local kernels?
So locality is not really the problem here. What you really need is smoothness in both directions, independently. That's really the key for those types of methods. But for instance, if you have a diffeomorphism, which can be represented as a linear operator, it will not work at all, because you completely break those smoothness. So for instance, I'm also working with deblurring problems in stray light, and stray light is when you have multiple reflections within a device, and it's completely not working there because you also have you have plenty of troubles. Yes, the smoothness assumptions are broken. You definitely need those smoothness assumptions, otherwise it's not working. And for instance, people in computer vision tend to use these methods, and they should not, because the PSFs do not vary smoothly in computer vision. So that's a mistake from an approximation theory point of view. Yeah, so it's working for microscopy, astronomy, so something, but it's not working in many cases.
Some more questions, comments? If not, thank you very much.